So let's start the second session with, we have two nice tutorials. I hope everybody's okay with the audio and video and so on. Okay, if so, let me introduce Andreas Dechant. He's in Kyoto University, and he will give the first tutorial on very hot topic, thermodynamic uncertainty relations. So Andreas.
Thank you very much for the introduction. And I'm also very happy to be a part of this workshop for the second time. And I think it's always a very useful and very inspiring occasion. So today I'm going to talk about the by now famous thermodynamic uncertainty relation. And so first of all, a warning, my talk is going to be a little bit technical because this being a tutorial, I want to show you actually how we can derive the thermodynamic uncertainty relation. But I will also make a few more general remarks about how we can interpret it. So what is actually the physical meaning, and I will give you sort of three different viewpoints on how we can understand this relation. And also in the end, a little bit about how we can generalize it. So where can we go from here? So maybe as a first motivation, so why is the thermodynamic uncertainty relation interesting? You all know the second law of thermodynamics, which describes a macroscopic system which is in contact with some thermal environment at some temperature T. And for such a situation, the second law of thermodynamics tells us that the entropy change, so the change in the entropy of the system, plus the heat transferred from the system to the environment divided by temperature, is positive. So this combination is always positive. And it being positive, we can just define this as some quantity sigma, which we call entropy production. And the physical interpretation of this quantity sigma is the change in the entropy of the universe. So everything, if you take the entire universe as a closed system, then the second law of thermodynamics tells us that the entropy of this closed system can only increase. And of course, the very fascinating thing about this second law of thermodynamics is that it is valid for any macroscopic process. So this means as long as we are considering a system which consists of many degrees of freedoms, this always has to hold, and there's no way around it. However, being so general, there's one trade-off in a sense, because the second law of thermodynamics by itself doesn't tell us anything about the size of the sigma. So how large does this entropy production or this change in the total entropy of the universe actually have to be? And of course, the reason is that thermodynamics by itself only tells us something about equilibrium processes, whereas any process that actually has a positive sigma is by nature a non-equilibrium process, so we cannot really make any quantitative statements about this quantity just using thermodynamics. However, in most cases, actually, we don't want to discuss completely general processes. So in most cases, we actually have some specific process in mind, and this means we actually have more information about the system than just being some macroscopic process. And examples of this may be, so we've already learned about steady states. So the system may be in a steady state. And so this is something that you can observe. So if, for example, if you consider a problem of heat conduction, so where you have a hot bath and a cold bath attached to your system, and then if this temperature profile doesn't change over time, then the system is in a steady state. There are also more sort of theoretical considerations. So for example, we know that if we consider the motion of a small particle in a liquid, then this is very well described by the overdamped diffusion. So this particle will just diffuse. So we actually have a very good sort of theoretical understanding of how we actually can describe the system. Or from an even more theoretical perspective, we may know that the system is described by some kind of Markov process, so that there is no memory in the system. And the question is, given this additional knowledge about the system, can we make any statement about relations between measurable properties of the system and this quantity, so this entropy production, so the change in the entropy of the universe. And the thermodynamic uncertainty relation is very powerful because it allows us to do just that. Because what we do is we consider some quantity. I will define precisely what I mean by this later. So this is a time integrated current. But for now, let's say examples of this quantity are the displacement of a particle. So for example, we're watching some particle diffuse and we just track the displacement, so from the initial point to the final point. Another example of such a time integrated current is the heat flow. So how much heat is flowing out of the system into the environment or from the environment to the system. And since we're dealing with stochastic thermodynamics here, so we're generally dealing with rather small systems which are in contact with some larger thermal environment, this quantity J, so the displacement of a particle or the heat exchange, is going to be in general a stochastic quantity. And as always with stochastic quantities, we have to use statistics in order to describe them. And the most basic statistics of such a quantity are its average value. So if we repeat the same experiment many times, how far is the particle going to move on average? And of course, then we also want to characterize the fluctuations, and the fluctuations are characterized by the variance of this quantity J. And the thermodynamic uncertainty relation tells us that this combination, so twice the average of this current squared divided by the variance of the current, is always a lower bound on the entropy production. Or I need to be more precise, this relation is valid in the steady state of a time reversal even continuous time Markov process. So if you think back to Simone's talk, so he also said that we are generally not considering things where, for example, the rates in our system have some strange property under time reversal, so are all under time reversal. And this quantity, so this relation between this measurable quantity J and the entropy production can be understood as a quantitative version of the second law, because this gives us a non-zero lower bound on the entropy production. So this means that as long as our system satisfies some certain conditions, we know if we measure this average and variance of the current, then the entropy production has to be at least this large. And so there are different ways how we can actually interpret this quantity. One way is sort of from a more fundamental theoretical point of view, we can consider it as a fundamental trade-off between precision and dissipation. Because if you look at the quantity on the right-hand side of this TUR, this is the ratio between the average current and the fluctuations of the current. And this quantity measures how precise the current is. So maybe it's easiest to imagine if J is the displacement of a particle. If this quantity is large, this means that the particle moves a lot, but it fluctuates very little. So this means when we repeat the experiment, every time we will find the particle more or less moving in the same direction. And this means that the process is actually very precise, because every time it does the same thing again and again, even though, of course, there are some fluctuations. On the other hand, if this quantity is very small, this means that the variance is much larger than the average. And this tells us that even though the particle may be moving on average, we will be observing moving to the right, to the left, to the right, to the left. So there's actually a huge amount of fluctuations. And this means what we're doing is not actually very precise. So between different repeatings of the experiment, we will get very different results. And the thermodynamic uncertainty relation tells us that this precision of the current is bounded above by the entropy production. And this tells us that if we want to have a large precision, so if we want our experiment or our process to be very reproducible, then we also need a large dissipation. So we need to pay a lot in order to really get precise motion. From a more practical point of view, we can also think of the TOR as an estimate on the entropy production, because this quantity J and the fluctuations of this quantity J, those can be measured. Whereas in general, the entropy production may be difficult to measure, in particular for small systems where directly measuring heat is actually quite challenging. And this means that using these experimentally accessible quantities, we actually get a non-zero lower bound on the entropy production. And as I will discuss later, in some cases, this bound can be tight. And we will discuss a little bit about when it can be tight. So when is this estimate actually good? Okay, so now let's get into the nitty-gritty details and try to actually derive this QR. And the system I'm going to work with is overdamped Langevin dynamics, because for me this has, in a sense, the most straightforward interpretation, because you can really just think of a small particle which is moving in a liquid, and we apply some force to this particle and force it to move. And then we ask, what is, for example, the displacement of this particle and what is the entropy production? This type of system is described by the overdamped Langevin equation. So, as I said, we have a Brownian particle. We consider the position of this Brownian particle, and this Brownian particle is in contact with some heat bath, which is just the liquid in the environment. And the motion of this particle is described by this Langevin equation. So this essentially tells us that the friction force is balanced with the systematic force. So, for example, this is what we use to drag the particle. But there's an additional term which includes this random force psi, and this essentially quantifies. This tells us about the thermodynamic, the thermal fluctuations in the environment. So you can imagine this particle sitting in a liquid, and the particle is rather small, so the molecules of the liquid bounce into this particle and kick it around a little bit, and this effect is described by this random force. Because it's sometimes a little inconvenient to work with these stochastic differential equations, it can be nicer to express this in a different but equivalent way. And so instead of the actual position of the particle, we are now going to talk about the probability density of observing the particle at position x at time t. And this probability density also changes with time in general. And this time evolution is described by the Fokker-Planck equation. So this is a continuity equation with the time derivative equal to the divergence of some current. And the current, in this case, is expressed by this local mean velocity, which is essentially some kind of, which you can think of some kind of effective force acting on the particle, times the probability density itself. So we're going from the stochastic equation of motion for the position to a deterministic equation for the probability. And within this framework, we can relatively conveniently discuss the properties of this time evolution, so how this actually looks like. And one crucial property of this time evolution is that it's Markovian. So it does not depend on the history of the process. So the precise statement is this. So this tells us, let's suppose we observe the particle at some position z at time r and at some position y at time s, and we want to know what is the position at some later time t. And the Markovian property just tells us that this probability only depends on the last observation. So in a sense, we can forget about everything that happened before this time s, and we only focus on the last measurement that we made of the particle, and this already tells us everything about the probability going forward. And this Markovian property allows us to think in a useful way about path probability densities, which Simone already introduced in his talk. And so a path probability essentially, so let's first discuss what is a path. A path just means that we have sort of a series of observations. So we observe the particle at position x0 at time t0, at x1 at time t1, and so on until some finite time. And because of this property, so the next observation only depends on the last observation that we made, we can factorize the probability of observing such a path into a product of transition probabilities. And what's even nicer is that for the Langevin equation, at least for short times, we can actually write down an explicit expression for this transition probability. And this is just given by this Gaussian probability density. And so here I introduce this quantity d, which is essentially the diffusivity. So this is just t divided by the friction coefficient. Now, how can we use this to get to entropy, and we already know the recipe, because we can talk about, in a sense, this statistical irreversibility. So again, we consider the forward path and some time reversed backward path, so observing the same trajectory in the opposite direction. And we can define the entropy production via the probability of this time reverse path. And this is just done in terms of this Kalbe-Gleiber divergence. And so, as we already heard in the previous talk, so the Kalbe-Gleiber divergence is essentially a measure of distinguishability, so how different two probability densities are. And this is always positive, and it's zero only if the two probability densities are the same. And what this tells us is that if we observe that the probability of the backward path is not the same as the probability of the forward path for some paths, not necessarily all of them, then the entropy production is always positive, and this means the system is out of equilibrium. Now, for the Langevin equation, we can actually calculate this quantity explicitly by using this expression for the short-term probability that I had 2 slides before. And what we find is that indeed this quantity on average gives back the second law of thermodynamics. So we have the change in the Shannon entropy of the system. And we have this quantity, which is essentially the force times the velocity integrated over time. So this is the total work done by the force. And this we interpret as the heat exchange between the system and the environment. And so this definition in terms of the path probability of entropy production actually reproduces the thermodynamic second law. For later use, I'm also going to introduce an alternative expression. So these are actually equivalent. You can show that those are exactly the same. And this alternative expression expresses the entropy production as the time integral over the magnitude of the local mean velocity. And the nice thing about this expression is that you can explicitly see that it's positive, because it's just the average of something squared, which is always positive. Now, the next thing we need to introduce, in the beginning, I said we want to talk about currents and the relation between currents and entropy. So we need to define what we actually mean by current. But we already had one example of a current, which is the stochastic heat. So since we defined this quantity as the average heat exchange between the system and the environment, it's natural to define this quantity inside the average as the random heat. So this is the heat along one trajectory. And you can think about it a little bit. So this is actually completely analog to the result that we had in the first talk for a jump dynamics, only here for the continuous case. And in analogy to this, we define more general currents by introducing some kind of weighting function. And we multiply this weighting function by the velocity, integrate over time, and the result we call a current. And again, so it's simple. Some useful examples of this are, if we just consider the unit vector in some direction, then this current is just a displacement. So this is just the difference between the initial and final position in this direction. Or, for example, if we consider this weighting function, so which is the local mean velocity itself, in this case, this quantity is equal to the stochastic entropy production along one trajectory. And the important property from the point of view of averages is that the average of such a quantity is given by the local mean velocity. So this local mean velocity that was defined in the Fokker-Planck equation appears again here in the definition of this current. And again, so the practical relevance of this is that these currents are actually the measurable consequence, in a sense, of everything that's happening, so of all the local transitions in the system. So maybe we cannot observe all the local transitions in the system, but we can measure sort of the global displacement of the particle, so how far it actually moves. So these currents are the things that we can actually measure. And so up to now, everything has been quite general, but now I want to focus on the steady state. So again, we assume that for long times, the system relaxes to some steady state, and under rather general conditions, this actually is true. So, and the steady state is also unique. And Of course, the steady state is independent of time. So the time derivative of the steady state is 0. So this means the equation determining the steady state is this condition, so that the divergence of the steady state current should be 0, where the steady state local mean velocity is just defined in the same way as the time-dependent local mean velocity, only with the steady state probability density here. And you can immediately see from the way that this equation is written, there's actually a very simple transformation that we can do that doesn't change this equation at all. And this transformation is rescaling the local mean velocity. So we just multiply this mu by some constant theta. And since we can take this constant theta out of the derivative, so it doesn't change anything since 0 is still 0. This means that if we have some system in which the local mean velocity is theta times the local mean velocity of the original system, this system is going to have the same steady state. And this is true for all, no matter which value of theta we choose. But this actually only holds for the steady state of the system, because if we look at the averages of currents, for example, then because as we saw before, the average of the current includes this local mean velocity explicitly here. And since we multiply this by theta, we also multiply the overall value of the current by theta. So this means, essentially, this just tells you, if you increase all the flows locally in the system, so if you make everything a little bit faster, then also the current is going to increase by the same amount. So I think this is quite natural. And now the question is, how do we actually get to this result? So how can we actually realize this local mean velocity times theta? And here it's important to note that actually multiplying by theta is the same as adding an additional force to the system. So here I just write this new theta, which is theta times nu, in a trivial way as this. So this and this just cancels. So this is just a definition. Now I plug in the definition of this local mean velocity. So the force, and here is the gradient of the log of the probability density. And I define this additional term, which appears here, as a new force. So I call this force g theta, which now depends on theta. But you can see formally, all I've done is I've added a particular choice of a force to the system. And now with this new force, we can again consider the Langevin equation. So we now consider a slightly changed Langevin equation, where instead of the original force, we now have this additional force g theta. And as we just saw, all of these Langevin equations actually have the same steady state by construction, because this g theta doesn't change the steady state. But the local mean velocity is multiplied by this value theta. And in particular, there are three choices of this parameter theta that give us some sort of directly physically meaningful result. The first one, if theta equals 1, if you go back to the definition, so if theta equals 1, then this force g theta is just 0. So we are actually back at what we started. So this is just the original system. On the other hand, if this theta is 0, then because the local mean velocity is just the original one multiplied by theta, this is of course 0. But since the entropy production was just the average magnitude of the local mean velocity, this is of course also 0. And this means that we are actually in an equilibrium system. So this means if we add this force g theta with theta equals to 0, we get an equilibrium system which has the same steady state as the original system. On the other hand, if we now choose theta equals -1, then you can easily see so all the local flows are just reversed in the direction. So in a sense, if the particle is moving this way, then in the dynamics with -1, it's going to move this way. And you can actually show that in the sense that the KL divergence between these two quantities is 0, the path probability for this force with theta equals -1 is exactly the same as the path probability of the time reverse trajectory. So in that sense, this dynamics at theta equals -1 just produces the time reverse trajectories of the original system. And so this is sometimes called the dual dynamics. And this means in terms of this quantity theta, we have now defined a continuous operation which connects the forward and the time reverse process. And so this we call continuous time reversal. This actually has some other properties which are quite nice, but I'm not going to discuss them here. And you can think of this property as a special symmetry of the steady state of a Langevin equation. So this means that multiplying this local mean velocity by theta doesn't change the steady state. So in a sense, we have a whole family of systems which have the same steady state and which are parameterized by this quantity theta. And if we go from theta equals 1 to theta equals -1, we go from the time forward to the time reverse dynamics. Now, we want to connect this to entropy production. And for this, we first need a mathematical result. And this was already mentioned in the previous talks. This is called the Cramér-Rao inequality. And so the setting here is the same as what we just heard. So we have some probability density on some state space. And now theta is some parameter. So in this case, I'm just using one parameter. So I'm not talking about any complicated geometry. So my parameter space is just a line. And then I define this average with superscript theta as just the average of some observable, which depends on the state of the system, at this parameter value theta. And in terms of this average, the Cramér-Rao inequality tells us that the derivative of this quantity z theta is related to what's called the Fisher information, which we also encountered before, in this way. So the derivative of the average squared divided by the variance is always less than this Fisher information. And interpretation of this is, if you think about what this quantity actually tells you, this tells us how much information about this parameter theta can we get from measuring z. So for example, if this derivative is 0, this means that z does not depend on theta. So no matter which value of theta we are, if we measure z, we always get the same result. And this means we cannot get any information about theta by measuring z. On the other hand, if this quantity is very large, this means that this quantity z depends very sensitively on theta. So even changing theta a little bit changes z a lot. So this means our measurement is actually quite sensitive to theta. So we can get a lot of information. And what this inequality just tells us is that the information about theta that we can get from measuring z is less than the information that's contained in the probability density, which is quantified by this Fisher information. So I think this is quite natural. And there's a simple proof of this inequality, and this just uses the Cauchy-Schwarz inequality. So we can write this change in the average like this. And so this is now the square of an average, and the square of an average is less than the product of the squares averaged. So we can take the square of the first term, average it, can take the square of the second term, average it. And this is just, so the first term is of course just the variance of z, and the second term is just the Fisher information. So this is the proof of the Cramér-Rao inequality, if you want. Okay, so now we know this Cramér-Rao inequality. What can we do with this? So now we want to go back to our original problem. And so in this Cramér-Rao inequality, we had essentially three things that we can choose. So first of all, this is capital omega. So this is just what is actually the state of the system. So what do we call the state of the system? Then we have this parameter theta, and we have some observable that we want to measure. And now the choice that we're going to make is to choose this omega as the space of trajectories. So in a sense, the state space that we're looking at is now the space of all possible trajectories that the system can take. And in this case, this P of omega is just the path probability density of the system. Now for theta, we already have a theta. So we just take this one, which is this continuous time reversal parameter. And we already introduced our observable, which are these time integrated currents. Okay, so now we've made our definitions. Now we can start calculating. The first calculation is very simple. So we already know that the average of this current at parameter value theta is just theta times the average. So if we take the derivative, we just get the current itself. And so the Fisher information, so this is just the definition. And now we need to somehow evaluate the derivative of this path probability. But let's recall that we actually have an explicit expression for the transition probability for short times. And so now with this parameter value theta, all I have to do is I have to add this force g theta. And otherwise the result is completely the same. And then the second thing that we have to remember is that we can decompose this path probability into just a sequence of transitions. So we can only have to consider a product of these transition probabilities. And this means that the logarithm of this path probability actually goes to a sum of the logarithms of these transition probabilities. So we only have to do this calculation once. And with this information, it's very easy to take the derivative because the log of this is essentially just the thing that's in the exponent. So we just have to take the derivative of this, since this doesn't depend on theta. And the derivative just looks like this. So we have this expression in the exponent times, using the chain rule, this derivative of g theta. And we have to take the square of this and sum over all the steps. Now, this difference between the position at step k plus 1 and the position at step k, for short times, this is just essentially the velocity times the time difference. And if we go back to our equation of motion, let me go back to the Langevin equation. So we have this minus this. So this is just this term. So what's written here is essentially just the noise multiplied by this derivative of g. So this means in the continuous time limit, so if we now make this dt shorter and shorter, we can write this as the square just as this integral. And so for clarity here, I once used the variable t and I once used the variable s for the time integral. But this is just the square of this integral. And now I want to take the average of this quantity to get the Fisher information. But this is actually becomes very simple because the property of this noise, so this is a white noise, so actually the values of this noise at different times are completely independent from each other. So this is just this delta function. So actually I only have to compute one of these integrals because they only because I only get a contribution if the two times are the same. And then I can just calculate this very easily. And I find that this Fisher information of the path probability is just the average over the derivative of this additional force squared and integrated over time. Now let's recall the definition of this force. The definition of this force was just gamma times theta minus 1 times the steady state local mean velocity. So the only dependence on theta is actually here. So if we take the derivative with respect to theta, we just get the local mean velocity. And we get the result that this Fisher information of the path probability is actually just 1/2 times the entropy production. I will give you a little bit of an interpretation on the next slide, so why this happens. Now, okay, so now we have calculated everything. We've calculated this. We have calculated this. So this is just the variance. So this means now we can use this Cramér-Rao inequality, and we find this. So again, so the derivative of j theta is just theta itself, and I theta is just the entropy production. And now this inequality, since this is just derived from the Cramér-Rao inequality, has to be true for every value of theta. So we may as well choose theta equals 1, which, as we said before, is the original system, and we have the TUR. So this means that now for the Langevin dynamics, we've actually proven the TUR, and this is valid actually at any time, as long as the system is in a steady state. Now, this approach using the Cramér-Rao bound doesn't only allow us to derive the TUR, but it actually also gives us a new interpretation of the TUR in terms of information theory. Because, so what is this parameter theta that we're looking at here? the parameter theta is just multiplying the local mean velocity. So this means essentially we are changing how fast everything in our system moves, or we're changing the magnitude of all the local flows in the system. And then with the information, with the interpretation of the Cramér-Rao bound that we had before, the left-hand side is the information about this change contained in a measurement of the current. So how much does a measurement of the current tell us about the local flows in the system? And the right-hand side is the information about these flows, so about this local mean velocity contained in the path probability, and this is equal to the entropy production. So there are two statements. So first of all, the left-hand side can be interpreted as the information we get about the irreversibility or the local flows in the system from measuring a current. And the right-hand side, the entropy production. So the right-hand side, the fact that the right-hand side is the entropy production tells us that the entropy production contains all the information about these local flows. And of course, with this interpretation, again, the inequality is sort of obvious because it just tells us that what we get from measuring something can only be less than the total information contained in everything. So in a sense, we will always miss something, and this is the reason why we have this inequality. Okay. So the next thing I want to talk about, what we can actually learn from this derivation of the thermodynamic uncertainty relation, is something about when this relation can actually be an equality. And so the question is, can we find some j that gives an equality? And of course, from a practical point of view, we want to know, is it possible to actually accurately estimate the entropy production? So can we, or at least in principle, can we find some current that gives us exactly the entropy production when using the TOR? And so unfortunately, in general, the answer is no. But why? So what is the reason? And this is actually related to this question of choosing other values of theta, because what you can show is that in the long time limit, the variance of j in the original dynamics is always larger than the variance of j in the theta equals 0 dynamics. And again, so theta equals 0 means we have an equilibrium system with the same steady state. And so this means, in a sense, we have excess fluctuations in non-equilibrium systems. So the fluctuations of currents are generally larger in non-equilibrium systems than they are in an equilibrium system which has the same steady state. And this means that in this, so at least in the long time limit, we have this sequence of inequalities. So because this is larger than this, so the variance is larger than this variance, so this is smaller than this. But for other values, but this is valid for any value of theta, so in particular for theta equals 0. So this is also smaller than the entropy production. And this actually tells us that if this is larger than this, we cannot get equality here, because in a sense we have an intermediate quantity that's already larger. And actually you can show that there's actually a positive term relating these two. So this means this is in non-equilibrium systems, this is strictly larger than this. And this means in general non-equilibrium situations, we cannot find a j that gives us equality. However, what we can show is that we can get equality in this relation. So in a sense, if you consider the fluctuations of this observable in this sort of if you want equivalent equilibrium dynamics, because if you choose j as the stochastic entropy production, then you get equality here. And well, of course, in a sense, this is also a little bit not so encouraging, because if we choose the stochastic entropy production as the observable, then we already know the entropy production. So there's no point in estimating it. But at least this tells us that, so in this inequality, we can in principle get an equality. So this is actually tight, whereas this is generally not tight. So what I just said, so this relates to arbitrary times, but the story is actually a little bit different if we focus on short times. Because in this case, we can derive an explicit expression for the variance of j. And this is actually quite simple. So this is just proportional to time, this diffusion coefficient that I just introduced before, and the, in a sense, average magnitude of this weighting function W, which defines the current. And you can see this is actually independent of theta, because this only depends on the steady state, which is the same for all values of theta. So for short times, the variance of this current doesn't depend on theta. And this means that for short times, if we choose this quantity J as the stochastic entropy production, then we're going to get equality. So this means for short times, if you're really focusing on a very short time limit, we can actually, in principle, estimate the entropy production perfectly using the TOR. And I'm going to skip the details here, so you can look at this later if you want. I have added a link to the slides. So in this case, actually, the TOR is very easy to prove because it's just the Cauchy-Schwarz inequality. Now, some a little bit hand-waving remarks about how tight is this bound actually. So we saw it's not an equality. So how tight is it in general? And so to measure the tightness of this bound, we can introduce this ratio eta j, which is essentially the ratio between this lower bound and the true value. So this is less than 1. And so one particularly simple case is bias diffusion. So if you just have a particle diffusing in a liquid and you just move this particle using a constant force. And in this case, you can show that this ratio is actually 1. So in this case, if you measure the displacement of the particle, then you can actually perfectly estimate the entropy production. On the other hand, if you choose a periodic potential with some bias force, so you can imagine some periodic potential, and you tilt this periodic potential, so the particle moves down the potential on average. And in this case, you can show that this is close to 1 actually both for small and for large bias. And the reason is a little bit different. For small bias, the reason is that the system is close to equilibrium. And you can also show that in principle close to equilibrium, because in this case also the variance is almost the same as the variance in the equilibrium system. You can reach equality. And also for large f, this is close to 1. And the reason is just that for large f, essentially the potential becomes negligible. So the system just behaves like free diffusion. And for free diffusion, we already know that we can reach 1. And so for, let's say, typical values, so for if the temperature is something like, let's say, 1/2 of the depth of the potential, and for sign potential and sort of moderate tilts, this is sort of, well, around 0.2. So in a sense, this estimate is not completely accurate, but also the order of magnitude is not completely wrong, at least in the simple system. And then finally, there have been some studies examining this ratio for some molecular motor models. And in this case, you typically find values of around 0.1 to 0.4 if you measure the displacement of the motor. And so again, the bound is not completely accurate, but the magnitude is okay. And maybe a final remark on this topic. So generally, if you want this ratio to be close to 1, then a necessary condition is that the statistics of your observable J are Gaussian, so described by a normal distribution. If it's not a normal distribution, then there's no way you're going to get close to 1. And I will also show you the reason why in a minute. I'm going to skip over the next few slides. Essentially, the point is just that for a Markov jump process, we can show exactly the same relation. So what I discussed now was for a Langevin equation. And so you can find some details of the proof. So how do we define this local mean velocity and so on in these slides. And so there's one thing is that during the derivation, we actually need an additional inequality. So for a Markov jump process, the bound is actually generally less tight than for the Langevin case. So maybe let me give you an intermediate summary on this part, so on the derivation. So we derived the TOR from this information-theoretic Cramér-Rao inequality. And for the proof, we needed 2 ingredients. First of all, that the steady state is invariant under this uniform rescaling of the local flows. So in a sense, if we make everything faster, everything flowing faster, then the steady state doesn't change. And that the Fisher information of these local flows, so how much we change these local flows, is related to the entropy production. And if we can establish these two conditions, then we generally have the TUR. And this immediately implies that we can now think about two types of generalizing this relation. First of all, since we saw that the TUR is generally not an equality, we can try to derive tighter bounds while keeping the same conditions. So can we get something that is actually an equality? And the second thing you can do, of course, is to think about now we drop some of these conditions and see what happens. So can we still get something that looks like a TUR, and how do we have to generalize the system? Okay, so this essentially concludes the part on the derivation of the TUR. So now let's talk about some ways of actually generalizing this relation. And the first thing starts with an observation. So we saw that the TUR only depends on the average and the variance of the current. So as I said, one strange thing about the TUR is that it only depends on the average and the variance of the current. But now, if you know something about statistics, of course, you know that in general, there are also going to be higher order cumulants. So this, except, so if the distribution of the current is Gaussian, then of course we only have the average and the variance. But in general, we can also consider higher order cumulants. And these can be described in terms of this cumulant generating function. So this is defined as the log of the average of e to the h times the observable. And if you expand this in a power series in this parameter h, then you see that the first term is just the average. The second term is the variance. And so this is the first cumulant, the second cumulant, and the third term is the third cumulant, and the fourth term is the fourth cumulant, and so on. So the power series of this cumulant generating function are called the cumulants. And intuitively, these higher order cumulants, because they depend on higher order moments of this current, they measure how likely it is to have large and rare fluctuations of the current. So in a sense, if you have more large fluctuations than for a Gaussian current, then, for example, this fourth cumulant is going to be positive. And as a technical remark, so this is actually very closely related to large deviations. And maybe you know that the original proof of the TUR was done in terms of large deviations. So in a sense, this cumulant generating function provides the connection between these two approaches. And now again, we have to introduce a mathematical inequality. And this time it's an inequality for the Kalbe-Gleibler divergence. And what we're considering here is two probability densities, now at two different parameter values. So we're no longer considering the derivative, but actually two sort of parameters with a finite difference between them. And then you can easily show this inequality. So this is essentially just introducing this factor divide by p theta 2 multiply by p theta 2. And then use Jensen inequality. So the log of the average is larger than the average of the log. Computing this log, so this exponential term just gives you this. And the second term is just minus the KL divergence. So the Kalbe-Gleibler divergence between p theta 2 and p theta 1. And this means, so this is essentially the proof of this Kalbe inequality, which is a lower bound on the KL divergence in terms of the average and the cumulant generating function. And so since this is valid for any h, we can also take the maximum over all h. And actually, as we saw before, the Kalbe-Gleibler divergence is related to the Fisher information, which appears sort of as the leading order in the Kalbe-Gleibler divergence, or the second derivative, for small differences in theta. So if you expand this for small differences in theta, you're going to get precisely the Fisher information. And this then again goes back to the Cramér-Rao inequality. So we do the same thing as before. Again, we choose this theta as the continuous time reversal parameter, p theta as the path probability, and this z as the current. And we have the same scaling of the current as before. And now we can actually again calculate this KL divergence between p theta 2 and p theta 1. And this is again given by the entropy production times some factor. Now we plug this into the inequality that we had before. And this gives a lower bound on the cumulant generating function. But now we see that the left-hand side doesn't actually depend on theta 2. So we can maximize over theta 2 on the right. And if we do this, we recover the quadratic bound on the cumulant generating function that was originally used to prove the TOR. So in a sense, this shows you that this proof of the TOR and the previous proof, in a sense, give you the same results. Now we write this in a slightly different way. So I introduced the cumulant generating function of the fluctuations. And so what I mean is I just subtract the average value of j from j. And because this is constant, I can take e to the h times this out of the average, take the logarithm. So this is just the cumulant generating function minus h times the first cumulant. And if I plug this in here and solve for sigma, then I get a lower bound on sigma. And again, here I can choose theta equals 1, since this is valid for any theta. And I get this inequality. So this tells me that, again, I have a lower bound on sigma in terms of the average of the current and something that quantifies the fluctuations of the current. But now I no longer have the variance, but actually the cumulant generating function of the fluctuations. And you can easily see that this is related to the TOR, because here I'm taking the maximum over all h. And of course, this is larger than taking h to 0, because h equals 0 is just one special value. So the maximum over all values is generally going to be larger. And if I take the limit of this going to 0, then this just gives me back the original TOR. And again, this shows that, in a sense, this higher order TOR, which involves the higher order cumulants, is generally tighter than the TOR. And the two are the same only for Gaussian statistics. And so this goes back to what I said before. So you can reach equality in the TOR only if the statistics of your current are Gaussian. Because otherwise, this is going to be an inequality. So this cannot be equal to this. And another nice thing about this bound is you can actually show that this also gives you equality if you choose J as the stochastic entropy production. And in this case, the optimal value of H is 1. And in this case, you can use the fluctuation theorem, and you find that you actually get an equality here. So in a sense, this bound is really tighter because it always gives you, you can in principle always get an equality. And again, so you can derive the same results for Markov-Chain processes. And so the second generalization, I'm going to skip through the derivation. Essentially, this just relies on a more general expression for the Cramér-Rao inequality. And the basic idea is that instead of considering one current, you now consider several currents. And again, you can derive a joint TOR for different currents, and you can again show that this is tighter than a single current. So I'm going to skip through this part because I want to talk about finally one generalization, which is, I think, very nice generalization and very important generalization. Because so far we've always been talking about the steady state of Langevin or Markov-Chain dynamics. And of course, an obvious question is, what happens for time-dependent systems? Can we still do something? And just as a reminder, so for time-dependent systems, we have this Fokker-Planck equation. And again, we do the same transformation. So we rescale the local mean velocity, and you can actually show that the Fisher information is still equal to 1/2 the entropy production. So this doesn't change. But the main issue is that now this time-dependent state actually changes, because if you multiply theta here, then you also need to change p in order to keep the equation valid. But intuitively, changing this velocity, so this means you're changing how fast everything is moving, and intuitively this means you speed up your time evolution. So you make everything go faster, and you can actually make the statement precise because so an overall change in the evolution speed of the system means changing all timescales of the system. And so the internal timescales are related to this local mean velocity. But we also have external timescales. So we can run a protocol on the system. So we can, for example, change some control parameter. And this means that if we want to sort of get the right scaling of the equation, then we also should change the time of the protocol. So in a sense, if we make theta larger than 1, then we have to run the protocol faster. So in a sense, if we speed everything up, then we also have to speed the protocol up. And if you use this, you can show that the derivative of theta with respect to theta of this current can actually be written as a derivative of this current with respect to the total time. And so, again, using the Cramér-Rao inequality, we find a TUR for time-dependent systems. And just to show you that this actually gives back the original TUR, so in the steady state, the current is just proportionate to time. So time times the time derivative is just the current itself, so we get back the TUR. And the nice thing about this is that this actually also gives a meaningful bound for non-current observables. So we don't have to consider current, we can consider any observable here and get a lower bound on the entropy production by considering the rate of change. And the important thing is that, so what this tells you, so what this measures is actually the response of the observable to changing both the measurement and the protocol time. So for example, you measure for a longer time and also make your protocol slower, so that you start at the same point and end at the same point, but now over a longer time. And you measure how much the observable changes when you do this. So when you slow everything down or speed everything up. And this gives you some information about the entropy production. And then, so there are some other generalizations that you can do. One of them that was asked before is about underdamped Langevin equations. And so here, actually the situation is much more complicated, because for underdamped equations, you now have two types of currents. So you have reversible and irreversible currents. But the entropy production only tells you about the irreversible currents. So if you only change the irreversible currents, then even in the steady state, this means that the probability distribution is going to change because you're not doing anything to the reversible current. And what you can actually show that in this case, you can derive something that's similar to the TUR, but you have additional terms on the right-hand side. And depending on how you derive this equation, how you derive this inequality, these additional terms are either related to what's called frenesy, so in a sense, how much your system is locally moving about, or to the acceleration. And of course, acceleration is just what actually makes the underdamped case different from the overdamped case. And one important question, which was unclear until this paper, is whether this is sort of just a technicality, so whether the TUR actually holds and we just cannot prove it. But in this paper, it was shown that actually there are cases where the TUR can be violated for underdamped dynamics. And the reason is that if you exploit the coherent oscillations, which you have for underdamped dynamics, because you have an acceleration, so you can have oscillations. And if you exploit these oscillations, you can actually reduce the fluctuations and violate the TUR. And then finally, there is a second generalization. I'm not going into the details here because I'm running out of time, to discrete time Markov processes. And again, you find a generalized version of the TUR, which includes some modification. And there have been several other generalizations so far. So for example, for time delay systems, so where the system actually depends on its own history, or for magnetic systems, because magnetic fields are also a little bit strange with respect to time reversal. Maybe the most important recent results, in my opinion, are the generalization to open quantum systems, so that you can actually also now discuss quantum mechanical systems in terms of these types of uncertainty relations. Or another relatively recent story is that you can derive TURs also for things like access and housekeeping entropy in the sense of steady state thermodynamics. So finally, let me summarize. I showed you, so we discussed this TUR, which is a trade-off relation between dissipation and precision for steady state Markov systems. And one interpretation of this TUR is as a quantitative version of the second law, because it gives you a lower bound on the entropy production. And it does so in terms of measurable quantities. So we can actually use the TUR to estimate the entropy production using something we can measure in the system. And the derivation that we did actually relied on two key facts. The first one is that the entropy production characterizes the rescaling of the local flows. So in a sense, this Fisher information is related to the entropy production. And the second thing is that the steady state is invariant in the rescaling. And then you can change, so you can try to derive generalizations either under the same conditions and try to derive tighter inequalities, or you can relax these conditions and then obtain generalizations to other situations. And so the final thing I want to do is sort of provide a little bit of a perspective, because the TOR is just one example of what you could generally call thermodynamic inequalities. And other type, for example, you can consider other types of lower bounds on the entropy production. And again, the idea is that you want to have something measurable or something that is some simple quantity which allows you to give a lower bound on the entropy production. And one result in this direction are the so-called speed limits, which bound the entropy production by some distance between the initial and the final state. So you move the system from some initial to some final state. And there's different ways of measuring this distance, for example, in terms of Wasserstein distance or total variation distance. And the speed limits generally tell you that the entropy production is, maybe there's some constant here, larger than this distance divided by the time it takes. So this means if you go faster, you need more dissipation. And of course, also if your initial and final state are further apart, then you also need more dissipation. And a relatively recent approach was to actually obtain lower bounds from waiting time transition, from the waiting time statistics of transitions. And this is really a little bit different from the TOR, because in the TOR, you're just looking sort of at the average current across some transitions in your system. Whereas here, you're actually looking at the time-resolved statistics of the transition. So how do the transitions actually occur in time, and when do they occur? And then finally, of course, you can also discuss inequalities which are not related to sigma, for example, the kinetic uncertainty relation, which is a bound on the dynamic activity. Or there are also other types of speed limits, which essentially the goal is to give a bound on the time it takes to go from some initial to some final state. And you can also think about trade-off relations between response and fluctuations. So that, in a sense, the response of some observable is again related to the fluctuations of the observable. And so as a final comment that I want to make, so why actually study inequalities if we have so many nice qualities in physics? And so from my point of view, what's nice about inequalities is that they are fundamental constraints on what can and cannot happen in physical systems. So if you think back to the second law tells you that the entropy of the universe cannot decrease no matter what you do. And in a sense, the TOR is in the same manner. So if you are in a steady state from a Macronian system, then there is no way that you're going to get around this bound. So it cannot happen. So in a sense, this gives you a real tight constraint on what you can actually observe in an experiment and whatnot. And of course, in a sense, there are only so many ways of relating different physical quantities using equalities, because always something has to be equal to something else. But in a sense, if you relax this to inequalities, you can actually find many more relations that show some maybe unexpected relations between different physical quantities. And this, I think, is very nice, a very nice point of view of studying inequalities. Okay, I think I went slightly over time. So let me thank you for your attention. And so I have included a rather extensive list of references on the topic. So if you download the slides, then you can read on your own time if you want. Thank you very much.